Russ Barlow is his name, and we're going to have him come up here in just a minute. But just wanted to mention again that he is the editor of the Universal Model. In fact, we call him our chief editor. And he's been a very important part of the process in making this book readable and interesting for all who will read it. So help me welcome Russ Barlow.
Thank you, Courtney. All right, I'm excited to be here tonight. I can tell there's hundreds of you out there, but you know that's okay when you clap loudly and shout and whistle if you want, and that's okay too. I've actually been involved in this project for about 11 years, and it's a passion. I love science, I love geology, and I love nature and earth science. So I'm going to share with you some of that tonight. So I'm going to ask you a question, though, that maybe isn't quick to the understanding. What do you believe that you know is not true? Now, I've asked some of you in the audience before. I see some friendly faces. So think about that, though. What do you believe that you know is not true? I would say nothing. Everything that you believe to be true. So that means the things that you've been taught or that you've learned or that you've read over the years form and shape what you think about the earth and the processes that go on. And we want to give you some new ideas to think about. So the first step, I want you to look at these two things right here, 2 dimes. I think everybody knows how much 2 dimes are worth, right? 20 cents, would you agree that they're worth 20 cents? Except there's something different about these dimes. If you notice, the date on the one that has the face out is 1963. In 1963, the dimes were primarily silver. So those dimes are not worth 20 cents. They're actually worth between $1 and $3 each. So with this new information, how many of you still believe that those dimes are worth 20 cents? Probably nobody. What you experienced because you had new information is you experienced a paradigm shift, a shift in your understanding and your knowledge because new information came. And that's what the Universal Model is about new information and a new paradigm. This happened for me about 16 years ago, 15 or 16 years ago. I was on a geology field trip with a professor from the local college here, and we were out there at Red Rock State Park, and we were looking at this red and white banded sandstone. And she posed this question: how did this red and white sandstone form? How did it layer together like that? And we were pretty excited, all of us that were together on this geology field trip. We were sure she was going to tell us how this was formed. But her answer was, we don't know. In that moment of serendipity, I knew that I would somehow know how sandstone formed. And I was so excited, I went back and thought I needed to buy some scientific equipment. My wife was a little bit scared. But I did not know that a few years later, after I'd taken a number of science classes, I happened upon this particular project that had a new idea, some new paradigm about how things were formed. Now, tonight, we're going to talk about some of those things. We're going to talk about melted rock and friction and magma. We're going to talk about Earth's energy field. We're going to talk about quartz and obsidian. And we're going to talk about sandstone and sand. We're also going to talk about the Meteor crater in Arizona. Many of you may have seen or been to that place. And we're going to talk about petrified wood and how to make fossils. I think everybody's wondered, how did those fossils really form? Now, let's start with a foundation. Let's start with where we are today. Where is modern science today? Well, we obtained this book. It's 100 scientists that shaped the world. This is not published by us. This was a book that's in the library. Anybody can get it. And we took all of the scientists and we listed all of their studies and all of their observations and theories and laws and put them into a table. One thing that we noticed, and it was kind of shocking, is that as time got closer to the present day, the number of new laws decreased to 0. while the theories continue to increase more and more and more. And so if we look at a zoom right here just in this last little while, we're in a scientific dark age, a period of which there's no new laws. Now, there's been lots of observations, lots of discoveries, lots of things because technology has allowed us to look deeper and look larger and smaller in every direction, but no new laws. Instead, theories have become the endpoints of science. We're no longer seeking for knowledge of laws. All we do is think of theories. And here's an example. One of the foundations of modern science started with this guy right here in the late 1700s, a guy named James Hutton. He came up with the theory of uniformity, which means the same thing happened over long periods of time. No longer was it fast and quick creation periods, but over long periods of time, and from that came the idea that the Earth is a hot, molten ball of magma. On top of that, a few years later, Darwin, when he read about this idea of uniformity, he published his book of evolution. And based on that, we know that man came from an ape-like ancestor, right? And we're taught that the apes came from a single-celled organism that crawled out of the ocean. Okay, that's the theory we know as evolution. But before that, the primordial soup consisted of the chemicals that made life. And the chemicals came from a place 13 billion years ago called the Big Bang. And the Big Bang came from nothing. And that's the theory we're taught today, is the theory of relativity. So we have these major theories of magma and uniformity, and we have evolution, and we have relativity. And from that, the entire modern science paradigm is shaped with those three theories. So nature's puzzle should look like this. If we were to put it together, it should be very defined. It should be a beautiful picture of what nature is. Now, modern science has a lot of these pieces of puzzle, but they've put them together in such a way that it does not make sense. It's disconnected and discordant with nature. And many of us in the world today have questions about how did that really happen? Even though the experts say certain things, we wonder, is that true? How do they know that? So truth is independent, though. It doesn't matter where truth comes from. It doesn't matter if it comes from a credentialed university or whether it comes from a grade school scholar. Truth is true. And because truth is independent of its origin, if we find truth, it will resonate with us. The universal model, the purpose of the universal model, is to restore truth and order in science by identifying new natural law, to return to its roots of years ago to law, to natural law, so that we can understand truth. The Universal Model book is divided into 3 major volumes. We've published only one so far, digitally. Volume 1 is the Earth system. It's about Earth processes and things that happen, like how rocks are made and how the Earth is formed and the things that shape it. Volume 2, which will be out sometime in the early part of 2017, is the living system. And in that, we talk about the laws of life and the age of the Earth and the process of how people moved around the planet. And then in Volume 3, the universe system, we talk about the fundamentals of things like mass and weight and time. So tonight, we're going to focus just on System 1, the Earth system. And that's the part about how rocks are made. So we talk about rocks, we talk about minerals, and we talk about water. And we're going to show how they all fit together in a very interesting and profound way. In the late 1700s, there was a great debate that was raging. It was between those that believed that the Earth was formed in a water-like environment. Scientists like Newton and Galileo and hundreds more like them believed for many, many years, even for centuries, that the Earth had been formed in a water-type environment. But by the 1700s, the Plutonists, or those who believed that the Earth was hot and old, came to light, and they began to debate and say, you don't know where this lava is coming from for these volcanoes. And the Neptunists couldn't answer that question. And so this debate raged until finally, because they couldn't come up with an answer of how the Earth produce this heat from volcanoes, it went the way of uniformity in magma. So isn't the interior of the Earth clearly hotter than the surface? We see volcanoes all the time, don't we? So we assume the scientists must be right when they declare that the Earth is a hot, molten ball of magma. But is that true? So James Hutton is the one who forms this idea that all geologists, all science students are taught today. And I would venture to say that everybody in this room has been taught this for so long that we just accept that it's true. How many of you have seen that? At least on, say, Discovery Channel. That's the magma, right? That's the proof that the Earth is hot on the inside. Well, there is molten rock, and so we have to, in our presentation and in our book, we talk about the difference between rock that is melted that's on the surface and rock that is under the surface that's melted, that we can see, we know it's there. There's no doubt about that. But what we want to define is the difference between the rock on the surface and right under the surface that we can see, that's observable, and the theory that deep inside the Earth, it's a hot, molten magma planet. Something like this, where the center is a solid core of nickel iron and the outer is melted and hot, and that's where all the heat comes from. Well, where does the heat come from, right? That's a question that the Neptunists couldn't answer. One of the reasons that they think today that the Earth is still hot and molten, because it's been around for 4.5 billion years, according to modern science. So there has to be some system, some process that keeps it hot and molten. The most commonly accepted theory right now today is that radioactivity keeps the center of the Earth molten because of all its heat. Now, we've heard of Chernobyl, the meltdown, and we've heard of all kinds of things that have happened when a nuclear reactor shuts down because of the heat. But if the center of the Earth was a hot, molten ball of magma that was heated and melted by radioactivity, then when that lava came out on the surface, the lava should be radioactive also. How many of you have gone hiking on a place where there's been maybe some lava and seen this warning sign? Anywhere in the world, there's no lava flow that has radioactivity, other than maybe trace background. There's no radioactive lava flows anywhere. So where did the radioactivity go? Well, this is a map of the world. If we see, it's divided up into plates, and you'll notice that there's a bunch of dots on there. Red dots here, and these look like black lines. Those black lines are actually made up of a bunch of little teeny dots, each one of those representing an earthquake, and each one of those red dots represents a volcano. So notice that all of the volcanoes happen along certain lines. Those lines mark the edges of the plate boundaries that are moving. The crust is cracked and fractured into plates, and as they move, that's where the volcanoes occur, and that's where the major earthquakes occur. So we know there's horizontal plate movement. That happens. We can measure that. But science also says that continents are raising and lowering over millions of years. But where does that vertical plate movement show up? Where do we see that? Better yet, where are the partially submerged continents today that in a million years will suddenly be up where we can have more land mass? If the continents are always raising and lowering, then some must be on their way down and some must be on their way up. But there are no continents that are sunk right now. All the continents are up. So how is it that some are raising and lowering in the past? Mount Everest is the poster child for uplift. It's the highest point on the Earth, 29,000 feet above sea level. And so important is it that we've installed little receivers where the GPS satellites can measure the teeniest movements up or down or sideways Mount Everest. But there is no up and down vertical movement over time. Now, there was recently an earthquake in the Himalayan plateau, and that was a sudden jerk, a movement. Those happen. There is no slow over time raising of these continents as they have supposed. At least there's no proof of it. So the nature and timing or even existence of magma oceans is uncertain, says an article in Geology in 2002. And in another one in 2004 in Nature, this is the prestigious journal of all science, said that the history of how the Earth's interior evolved is still a mystery. Taking water into account could help explain it a great deal more. And that's what we're going to do tonight, is we're going to talk about water and how it works together. But what if there was no magma at all? What if the Earth was not a hot, molten ball of magma at all? Remember that picture just a minute ago. Here's a question that we would ask. And you could ask the USGS is, do earthquakes cause volcanic activity? Those little black dots, those are the earthquakes. Do they cause the volcanic activity? According to the USGS, no. They're not the cause of volcanic activity. Earth scientists believe that most earthquakes are caused by slow movements inside the Earth. So this slow molten ball of magma slowly comes up and creates these earthquakes. But what does the science show us? What does the actual observable experiment show us? This is a survey of 600 earthquake swarms. An earthquake swarm is when about 1,000 earthquakes happen in a very short period of time, so that means there's a lot of movement. This survey looks at those, and if you'll notice, 55% of those earthquake activity preceded an eruption. So that means when they had an earthquake swarm, 55% of the time, there was an eruption that followed. There was another 39% that didn't produce any eruption at all, and there were 6% that had an eruption that happened, the eruption preceded, so the eruption happened before the earthquake activity. So to a great extent, the observations show that earthquakes are happening before the eruption. Now, how does that tie in, and why is that important? In the universal model, we introduce a number of laws of things that are observed based on science that's happened, and many times based on experiments we've done ourselves. In this case, we look at all their data and we just look at it in a different way, and we understand and see that friction creates heat. We know, everybody knows, friction creates heat. When your fingers are cold, you rub your hands together, you warm your hands by friction. Well, 10,000 feet of rock, that's about 2 miles is all. If it moves 1 millimeter, it creates enough heat to melt rock. So the frictional heat law is that friction, or rock moving against rock, produces heat enough to melt rock and make lava. But that happens in the crust. So the frictional heat law is friction creating heat to melt rock. And the evidence is all the way from just Yellowstone National Park. How many of you have heard the idea that Yellowstone, the Great Caldera, is a big magma chamber underneath that's about ready to blow, and we should be afraid of it, right? Well, Yellowstone is the most geologically active spot in the entire continental U.S. The reason that there's so much heat at Yellowstone is because there's so much seismic activity, so many earthquakes. There's another place, Jupiter's moon Io. That's the smallest of the 4 Galilean moons. It's a little moon that zips around inside it's the closest orbit to Jupiter of all of its many moons. The tug of the other moons and the giant planet Jupiter caused the surface of this little moon, little Io, to go up and down 90 meters every day. That's 300 feet. The surface of the Earth, of Io, is going up and down 300 feet every day. That creates so much friction that the entire surface of Io is like one giant melted surface. There's volcanoes that have been active there for as long as we've known them. Could I get that bottle of water? I'm sorry. It's right over there. Pardon me. So the gravitational friction law is the follow-up to that law. And it says that the gravity happens, or the friction happens, but something's driving that friction. And what drives the friction is the celestial bodies. Like we saw in Jupiter's moon, the tug of the other moons and the tug of Jupiter are stretching and flexing the crust, and that's what's creating the friction. What happens to Earth is the moon, as it goes around the Earth, tugs the surface of the Earth and pulls it into an egg shape. And as it does, it creates a lot of frictional activity. In fact, there's over 3,000 earthquakes every day on Earth that are measured. That's 3,000 every day. One of the things that scientists wanted to do is try to drill into and see magma. See, we've never seen magma. We've never seen a magma chamber. Everyone has always been either inferred or suggested, but we've never seen it. So there was a program where they wanted to drill into a hot area, a magma chamber, inject water, and then capture the energy from the steam that comes back out, create a geothermal pump or a well. And so they studied 22 different sites to determine the most plausible, the most likely place where this could happen. And they settled on Long Valley, California, which is over near Bishop, near the Sierra Nevadas. And so they set out there to drill down to this magma chamber that they thought was some between 3 and 6 kilometers below the surface. But the problem is when they got there, the closer they got to what they thought was the magma chamber, the colder it got. And so they finally realized after drilling that there was no evidence of magma at all, at least in the upper 10 kilometers. So that's not the deepest we've drilled, though. How about this one? In Germany, scientists drilled 9 kilometers. And then in Russia, they drilled 12 kilometers. It's about 7 miles down into the earth. Now, in the scheme of things, that's pretty small because it's 4,000 miles to the center of the earth, so drilling 7 is not very much. But they never found any magma. What they did find is that it got so hot at 12 kilometers down, they couldn't drill any further. And they noticed that there was friction happening. There was an earthquake that happened and it actually caused a heat spike in the hole, in the Kola borehole in Russia. So they did finally publish an article, said the more we drill, the more we find out how little we know. They did not find magma, but they did find the fault lines that when they drilled through, that it produced heat. They just didn't realize that that was the process that was producing heat across the world. Scientific American article in 2005, the article said, the textbook view that the Earth spent its first 500 million years drenched in magma could be wrong. Maybe the Earth wasn't a magma planet. Not from the evidence, anyway. So now let's move to another area, the center of Earth. The spinning dynamo in the middle of the Earth that supposedly is creating the Earth's magnetic field. This is what the textbook version looks like. The magnetic field is created by the flow of molten iron deep inside the Earth's core. But this is what it really looks like when we map the magnetic field of the Earth. It's twisted and gyrating, and in fact, if you look closely, you can almost see the shapes or the generalizations of continents. So what's creating that wild magnetic field if it's all being generated from the inside, from just one single spinning core? Another problem with a spinning core, before I get that, Einstein said in 1905, he said that the problem of the origin of Earth's magnetic field as being one of the most important and unsolved in physics, and it still remains so today. Nobody's really sure about how that magnetic field is being generated. The magnetic field also migrates. Each day, it moves 85 kilometers. That means it's not standing still. The field, the North Pole, is moving 85 kilometers. So if you had your magnetic compass up north, it would be absolutely worthless because it would be pointing here at one part of the day and there at another. And it also migrates every year. 1900, it started here. This is where it is in 2005. And the interesting thing is that right here in Las Vegas, how it affects us is that it used to be runway 24 that the planes would land on when they would come in from the east. They'd land on runway 24. How many of you know what that runway is today? It's runway 25. They had to renumber it a few years ago because magnetic north is moving so much that it's changing the numbering or changing the direction of the runways. The runways are numbered based on what degree they are facing. So 24 meant 240 degrees. Now it's 25. That's a pretty big movement, isn't it? The other problem is that heat destroys magnetism. If you have a magnet and then you put it and you heat it up, you'll actually cause that magnetic field. You'll lose the magnetism. The magnet will stop being magnetic by putting it in heat. And that's an unsolved problem. It's why the spinning dynamo doesn't quite work. It breaks down when you look at the physics of it. Experiments show that heat destroys magnetism and materials lose their permanent magnetism when they exceed only 500 degrees Celsius. That's not even the melting temperature of rock. So at 500 degrees Celsius, it loses its magnetism. So how does it create a magnetic field? Geologists still know nothing about the composition of the core from direct observation. So what is driving the Earth's magnetic field? Something is, right? Well, we're going to talk about quartz and how it fits in. Quartz is one of the most common of the silicates on the whole planet. It's silicon dioxide. And it's so common, it's found in nearly every geological environment. It's found everywhere, even in the sand. Almost every rock type, it's greater than 98% everywhere around the Earth. Here's the physical properties of quartz compared to glass. They're both the same. So quartz has a hardness of 7. That's not a big deal. That's not a big deal. But look at the thermal conductivity. Quartz conducts electricity. Glass, not so much, 0.7. But that's 720. Quartz produces electricity. How many of you knew that? If you melt quartz or melt rocks, it makes glass. It doesn't make quartz. So it couldn't be melted. In fact, if we look at this phase diagram that talks about the melt point, natural quartz forms right here. It doesn't get over that 1,000 degrees temperature. It doesn't get hot enough to melt. If it gets all the way up to the temperature of melted rock, then it's glass when it's cooled. And quartz cannot be grown from a melt. It can't be grown from a solution of melted rock because they form glass, not crystals. Which brings us to the rock cycle. Modern science tells us that all rocks come from a melt. And if you notice, all paths lead back to magma. Magma creates igneous rocks, which then get ground down into sediment, which becomes sedimentary rocks. And then it's changed through either metamorphism to metamorphic rocks, or it's ground up again and it's cycled. But either way, it all comes right back down to magma. So all rocks are melted rocks. Do you see the disconnect between quartz? It can't be produced from a melt, but yet science says all rocks come from a melt. Another thing is that quartz has a piezoelectric property. That means it has electricity. And what you're seeing right here, these two rocks, if you rub them together, can you see that little glow? If you rub rocks together, you can produce light. Afterward, I think we have some rocks here. You can see that. You could produce electricity by rubbing two quartz rocks together. We use quartz crystals in watches because the electrical current in there keeps your watch powered. Quartz cannot be grown from a melt because when you melt or get that rock too hot, it loses its piezoelectric phase. It doesn't have the electric phase if it gets too hot. Another part of quartz is the little teeny sand grains that pester us when we're trying to sweep up the house, but we love when we're going out in the sand dunes, right? Or standing on a beach. But we look to the west here and we see Red Rock State Park or Valley of Fire and we see red rocks. So the question is the sand red? Are the quartz crystals that make up that sand red? This is from coral pink sand dunes and from imperial dunes in California. So just gathering random sand. But if we look at it up close, look at that. That's what imperial dunes, look at the color of the sand. Look at the color of the crystals here at coral pink sand dunes. The crystals themselves are clear. Clear quartz crystals. And it's the stuff in between the crystals that makes it look red or brown. But the sand crystals themselves are clear. They're formed from a different environment than being melted or eroded. And did you know there's also quartz in fossils? We're going to talk about fossils tonight. Dean's going to bring up fossils like petrified wood and that. But if you notice right here, here's a dinosaur bone. And in the middle of that dinosaur bone, is agate, which is a quartz crystal. In this particular bone, this is calcite, another common form of crystal. Petrified wood is mostly quartz crystals, silicon dioxide. Most fossils are quartz crystals. The other thing we said we'd talk about is water. How abundant is water in the universe? How abundant is hydrogen? It's the number one element, right? And oxygen is also the most abundant element, one of the top 3 abundant elements. But when you put them together, H2O, that's where the abundance of hydrogen and oxygen is, because the most abundant element in the universe is water. In fact, the most important discovery since the space exploration began 25 years ago, says Elon Musk. He's the guy that invented the Tesla. He's also the guy that wants to take everybody to Mars sometime in the future. He said that discovering water ice on Mars was the most important. Now, how much water ice do you think there is on Mars? You maybe have heard about this, but look at this. Right here, 30 to 60% of water in the soil there. That's a lot of water. Mars has a lot of water. But Mars isn't the only one. Mercury, the closest planet to the sun, possesses between 100 billion to 1 trillion tons of ice, says NASA. Venus says there was once an ocean 100 times or more water. Jupiter, between humidity from water, between 4 and 8 bar. Uranus, below the clouds, are probably liquid water, maybe even an ocean. Neptune, scientists believe that Neptune is made up chiefly of hydrogen, helium, water, and silicates. You see water everywhere in all the planets, but it's not limited to just the planets. If we look at the moons of Jupiter, we talked about one of them, Io. That's the most active body in our solar system that is constantly being flexed and melted, but the others, they're not subjected to that same heating. And so NASA looks at that and sees that there's an icy crust, it has a sub-ocean, and it has an ice rock interior. These are NASA pictures of what they think the inside of those moons look like. Here's a Saturn, one of Saturn's moon. Cassini, a spacecraft, flies by and sees that and says that the surface of this particular moon has thick deposits of ice. But here's one of the coolest. This is one of Saturn's moon, Enceladus, and when Cassini flew through that, it recorded a little ice volcano. This is what it looks like in real time. This is what it looks like just so you can see how big that ice volcano is, spewing ice out into the space around it. That's water. That's a giant ice volcano for such a little moon, isn't it? So that's observable. We see water. And how about this one? This is a satellite. They sent it 1 million miles out into space to record and watch the sun. But when they first sent it out there, the lens was blurry. They were pretty upset because they couldn't see the sun. The other instruments worked fine, but the visual instruments were not. They were pretty disappointed. And then one day they lost control of it. It started tumbling. And as they gained control of the satellite, realigned it and pointed it to the sun, all of a sudden it was clear and they could see. And they realized that what had happened is that water ice had formed on the lens of that satellite. And so for the first time, they found that there was water far out into space, way above the Earth. So how does liquid water exist in the icy depths of space? It's supposed to not be possible, and yet there it was. In fact, it's the discovery that amorphous ice is more like liquid water than it is crystalline ice came as a huge surprise, it says in Scientific American in 2001. The inventor of the laser that I've been pointing, see that guy right there? A guy named Charles Towns, back mid-century 1900s, developed a maser, which was a device to look out into space and to narrow it down to capture these bursts of energy that they could measure that were coming from hydrogen. And they were excited. It proved it worked. And they said, well, let's tune it to the water line and find someplace in space. And so they turned the radio telescope to the Orion star cloud. That's where stars are supposedly being born. And they noticed this big spike. There was so much water that when they published the article, they said it must be raining in Orion. said Charles Towns. So where do you think the least likely place to find water would be? Of all the places that you can imagine water, where would you think it least likely to occur? They discovered water on the sun. You see the same thing here. We see the water line. There's water on the sun. In fact, in an article in Science in 2002, they said the water molecule plays a fundamental role in the first stages of star formation. So water is important in star formation. That's pretty cool. In fact, we find water everywhere we look. Water is in the planets, it's in the moons, Earth, the sun, interstellar space, the stars. Everywhere we look, we see water. Water is everywhere, and it is one of the most fundamental building blocks of the entire universe. So what would you say if someone told you that all natural rocks contain water? What if every rock that you went and picked up out there had water in it? Well, it does. This one's called an anhydro. You can see that water. We have a few of those. There's a little bubble right there, or a bubble right here. And when you tilt it, you can actually see the bubble moving in water, that water trapped inside the crystal. But it's also an obsidian. About 3% water is trapped in obsidian. So just an obsidian rock has got water in it. Opal contains 30% water. Pumice, you probably know what pumice is. It's really light rock. That's what happens when the water escapes. So the rock is heavy because it's dense and it has water in it. But if it cools in an environment where the water can escape, it turns into pumice. It's a frothy mix of just silicon rock, the same stuff that quartz is made of, but the water's gone, and so it's very light and airy. In fact, this is an example of a deposit where it has obsidian and pumice. The pumice is the light gray, and the obsidian is the glassy rock. At that point right there, that's when the water escaped out of some of this and just evaporated and caused that rock to become frothy and empty of the water that it had, whereas the water right next to it, that water's still contained in there. This is what a volcanic rock typically looks like. It's got holes in it. And so you pick up a piece of lava rock, it's very rough and coarse and it has big holes in it. Those big holes came because when that volcano erupted, the water that was trapped in those rocks expanded. Now water expands 1,700 times when it goes from a liquid to steam. And when it does, it just bursts and pop. It leaves holes behind in the rocks. So as we look at the evidence, when we look at how things are forming, the quartz crystals, the electricity, the water in the planets, we come to realize that the magma planet idea doesn't work. And in fact, there's an enormous amount of evidence that shows that our planet is a hydroplanet, a rock water mantle, a liquid outer core, and a solid ice inner core. Now that's a pretty big deal to talk about, but the book, the volume 1 is 800 pages, and if you want to read about that in there, you'll find the details of how we arrive at that in much more depth than we can talk tonight. So back to obsidian. Why did obsidian, that rock that has water in it, why is it sitting on the surface of the earth and not pumice? Well, because that rock cooled under 3,000 meters of water. It had to trap that in. It required the pressure of 3,000 meters of water to be able to trap the water in that rock. So now we have hot molten rock, and we have 3,000 meters of water. We're creating a very special environment, something that existed at a time in the past where we had heat and pressure and water. And that's called the hypertherm. So a hypertherm is a brand new word. You can't Google that word. It doesn't exist except in the universal model, so you'll see it in there. And what it is, it consists of hydro, water, pressure, and heat. A hyperthermal environment. And a hyperthermal environment is the environment in which minerals grow. It requires all of those ingredients. So this is what science tells us, that everything started from igneous rocks, from metamorphic rocks, and from sedimentary rocks. But sedimentary rocks are just ground up metamorphic rocks, right? Or igneous. So that's not an original rock. Metamorphic rocks are just changed by heat. Well, that's not an original rock. So all rocks are these igneous melted rocks, according to modern science. But our research and our own experiments and the things that we've done show that there's actually 9 new classifications of minerals. And the ones that are important are the ones in blue. These right here all required water. Those are the ones we're going to talk a little bit more about tonight. In fact, that hyperthermal environment is the environment in which we created quartz crystals. And later you'll learn it's the environment in which we created fossils. It all starts with this high pressure reactor. That's just a little pipe. It's about that big, you can see. Inside that pipe, we create a pressure zone of between 13 and 14,000 psi. This right here is a little seed crystal. Just take a little teeny crystal, we wrap it up in a wire, and we put it and hang it inside this pressure reactor. And this is what it looks like after one day. You see how the quartz crystal actually grew around the wire right there? Right there, the quartz grew right around the wire. In one day, we doubled the size of that crystal. Now, it took dozens and dozens of attempts to finally figure that out. And each time, you had to take that pipe apart, break all the stuff out of it, recreate the experiment, and try again until we finally got the thing right to where we could grow quartz crystals. You see how that's the wires kind of holding it and the quartz grew around that? So over time, we learned how to grow quartz crystals. And quartz crystals form fossils. And Dean's going to talk about that. So that's the foundation of where we are today, about magma and about the hydroplanet Earth. And so we've kind of built a foundation, and Dean's going to talk next. Courtney, do you want to come on up and introduce Dean? And I want to thank you for your time.
Thanks, Russ. Appreciate it. Great job. We want to introduce now to you Dean Sessions, who is the author of the Universal Model and the founder of Millennial Science. Dean started researching back in 1990 in the area of archaeology and found a lot of new things that haven't been discovered before in that area, and that research led him to other areas of science. As you have noticed here, all the different areas of science are connected, and when you start studying in one area, it leads you to another area. And over the years, even after he started writing, he found and discovered many different natural laws and things in science. As I say, he started in 1990 researching. He started writing the book in 2000. And we're happy to be able to introduce the first volume tonight. So if you would help me welcome Dean Sessions.
Thank you, Courtney. Appreciate that. Oh, it's great to be here tonight and have a chance to talk a little bit about the Universal Model and some experiences that we've had with it. We want to continue on a little bit with the hydroplanet model. I want to thank Russ. That was a really good job, even with his cough. It's a little hard presenting when you have that situation. But inside this hydroplanet model, we have a quote here from the New Scientist that tells us, "Deep inside the Earth, the pressure is excruciating. But it also contains something surprising. What's the last thing you would expect to find in this hellish environment? Water. Vast amounts of this stuff. In fact, no more than 400 kilometers inside the Earth there may be enough water to replace the surface oceans more than 10 times. How much there is down there is still fiercely debated. But these inner oceans could help to explain a long-standing puzzles about the Earth's formation. many different strands of evidence point to the existence of this hidden water. So what we see here is, obviously, modern science is beginning to realize that the textbook view could be wrong. This is another quote. The universal model, as explained earlier, has 3 volumes totaling more than 2,000 pages. It's difficult to take this information and bring it into a small time frame like we are tonight talking about it. But what we're doing is talking a little bit about Volume 1, which has been released to the public back in October. So just recently, we're brand new at this, sharing it with the world. This is something that's really never been done before, and it's exciting because we have an opportunity to talk about things such as a hydroplanet model. We never heard those words before and what they mean to us. The Kola well and our own have shown that the deep crust of dense hot rock is definitely not the case. There are large amounts of highly saline brine in the crust that migrate, carrying metals around and depositing them as minerals. So this was in Science, and this is, once again, Russ talked about some of the boreholes that were drilled earlier, and this is the kind of thing they're finding, is that they're not finding magma, they're finding water, in this case salt water. And this is an image of a tomography of Central America. So this is a cross-section, you're looking at the Earth, and you can see down here where the core is, it's supposed to be magma and really hot. The red is giving us an indication of really where the hot areas are, and the blue is the cooler areas. They find this through tomography. Is kind of like when you get a sonogram and a baby is being shown, you know, when the pregnant woman is going in and they can see the baby moving in there, they're using sound waves. Well, when the Earth has seismic activity, the sound waves going through it are recorded by stations all around the Earth, and this is the kind of thing that they're able to figure out. And the interesting thing is this is where the trench is. This is where the plates that Russ talked about a little earlier that go around the Earth, that's where the plates meet and where the heat is really taking place. These little white dots are earthquakes right here. And what we find is down inside the Earth, that big blue area, we call these hydroplumbing systems. In Greece, Brodsky has found that hot springs are fueled not by a magma chamber, but by the changes in the pressure of fluids coursing through underlying crystalline rocks. So once again, these are scientists that early on we found out that in the puzzle that was given, nature's puzzle versus modern science puzzle, we found that the modern science puzzle, there's just so many of these observations that we're showing you here tonight that the scientists find these and they try to put them in a cohesive, you know, in a puzzle that makes sense. The little pieces don't click together. And not only that, but when they do put some of them together, they don't make an image that's understandable. We can't comprehend it. And one of the reasons why is because of the theories that was explained earlier in modern science today. They're not looking for natural law in general. So what happens is these theories that have been now in place for more than a century they're not matching up the new observations, and this is just another example of that. This particular image on the right-hand side here, the black area, was out of another journal article. Those blue lines along there are all indication of water areas that were found, once again, through this seismic activity. Right below the upper crust, this line right here is all this blue shaded area has a high water content. Now, geologists will tell us that the plates of the Earth are actually floating. The question is, what are they floating on? If they're floating on magma, what would happen when you go down in the oceans and you get closer and closer to the magma? Obviously, the water would get hotter. Yet this is not what happens. If you go down deeper in the oceans, it gets cooler. And so this is just another example of showing what happens inside the Earth. This is a particular volcano that in Japan, the Miyake-jima volcano, you're seeing a cross-section there. And once again, this is out of a journal article, and all we did was color the area blue that they are indicating is full of water. This is a hydrothermal system inside the volcano. And it's a cross-section, like it says right here. And what happened when this volcano erupted was there was this plume, as you can see right here coming up. This is the little volcano here taken from a satellite. And it's amazing how much water is inside volcanoes. They actually have recorded 95 to 97% of what comes out of volcanoes is not lava like we see maybe in the movies or in our textbooks, but it's steam. Water, steam. This is really important. We all recognize what geysers are. Geysers are something like was talked about a little earlier in Yellowstone that happen every day. And in Yellowstone, Russ talked about the plates coming together. There's actually 3 areas that the plates are coming together, and that's really rare. Usually they just go along, and when you have plates, they come together, all pushing at that same spot. It's constantly causing friction. I don't think it was brought up yet, but this is called earth tide. And this is something modern science understands already. The earth tide that was talked about by Russ is here in North America, in Nevada, where we're at right now, about a foot. The ground we're standing on goes up and down every day about a foot. And this is because the Earth spins on its axis in 24 hours. And the moon, which is causing 2/3 of the pull on they call this the earth tide, and the sun's doing the other third. We all know tides come from ocean water being pulled by the moon. That's something we're all taught in school, probably, you remember that. But does gravitational pull only occur on water? Of course not. It occurs also on everything else around us. And when you have a large body like a crust of the Earth, it gets pulled up and down because the Earth goes around and gets farther away. The moon takes 27 days to go around. So as the Earth goes around in one day, this is what causes the constant tugging up and down. And it's this activity that gives us these heated waters in Yellowstone and around the world. Before we talked about Iowa a little bit, and that 100 meters, which is a tremendous amount. So there's so much volcanic activity on that moon that we have pictures of the lava from space. So you can imagine how much lava has to be on the surface of that moon. And now on the Earth here, it's much smaller, but we have evidence of this happening here with geysers all over the world. So we want to connect this to the weather model. The weather model is truly amazing because for the first time, we have 2 things to understand about weather that we've never understood before, and the understanding comes from this new geology. Think about that for just a minute. Who would think you have to know geology to understand the weather? The weather is about the atmosphere, right? So why do we care what's going on with the ground and underneath the ground? Well, it turns out that this is a very important topic. You can see here, these are all chapters and some of the sub-chapters in the book, and this whole section here, the weather model, we get into 2 different areas. One area is the origin of weather. It's the first half of the chapter. And the second area is the origin of the Earth's, what we call geofield. Russ explained before, a magnet loses magnetism if you heat it. So the Earth really doesn't have a magnetic field. It's an electric field, and this electric field is created by the piezoelectricity that Russ spoke of a little bit earlier. That piezoelectricity is caused because the crust is going up and down, like we spoke of a little bit earlier here. Not only the piezoelectricity is causing our Earth's energy field, but here we see the water cycle. This is how weather was supposed to be created. There was only one water source, one heat source right up here, and that's the sun. As you can notice up here, this is the old water cycle. This is by the USGS, or United States Geological Survey. And this is something we're commonly taught in school. Children learn it. And most of it is correct except for one thing. They're missing. We created a new water cycle because we found out they were missing a new water cycle. The second heat source is down here. You can see the two heat sources is what's actually creating weather. This second heat source is called a Hypertherm. So the high is from water, and the qua is from earthquakes, and the therm is from thermal. So a Hypertherm is what's happening underneath the crust. This friction and the heating, now that we know there's so much water inside the Earth, you can see how this water that's heated under there, Russ already explained, when it's liquid and turns into steam, it expands 1,700 times its volume. What does this do? Well, it expands and comes above the Earth, as you can see in this diagram right here, and it creates clouds. We actually have a whole section in this chapter that explains how earthquake clouds are formed. Immediately after the earthquake, a strange cloud appeared above the epicenter. So we actually document, there's one researcher out of California that found that he could look at clouds from satellite images and from those predict when an earthquake was going to occur. And he did this like 55 times. And the geological establishment doesn't really recognize it because it's not coming from magma. It doesn't. Earthquakes, remember, they're not supposed to be connected to clouds or anything like that, or creating another heat source. They're supposed to be coming from magma. So his research hasn't been very well accepted, but it fits right in with all of ours. Matter of fact, the Russians have found with their research that large areas, this is over across Japan right here, this island has been enlarged to what you see right here. And they were some of the first scientists and investigators to clearly establish the direct link between earthquakes, crustal heating, and the change in weather over the earthquake area. Now, when this water comes out, it's just not pure water. Guess what else comes out with it? Carbon dioxide. Where does that carbon come from? Well, there's a lot of golden threads that run through the universal model, and one of the golden threads happens to be microbes. Microbes are tremendously important in so many different science fields. Geology is just one of them. And it's through microbes that we come to find out that not only is carbon dioxide created from these microbes and other gases, but the microbes are also involved in creating the colors found in rocks. In the weather, what we find is we have these H's and these L's. And it's kind of fascinating because when the water comes up out of the ground and is creating these high pressure systems, we know, as it says right down here, the importance of our atmospheric pressure to Earth's weather cannot be overemphasized. So the pressure is really the key to understanding weather. When you have high pressure, it pushes all the air around out away from it, and it goes down here to these low pressure areas. This is something that meteorology recognizes and understand, but they don't fully grasp where the high pressure systems come from. And without this understanding, we can't understand weather. So we have local weather, and then we also have worldwide weather. Underneath the crust is where we're getting what we call endovaporization. This is where hydrotherms are creating this new high pressure system. But there's also something taking place underneath oceans. The continents are about 36 kilometers on average, their thickness, but we have under oceans about 6 kilometers. And that oceanic crust, when that friction takes place in there along fault lines, what you have happening is it's heating now the water that is coming out of the crust. It creates these plumes of water. And we can read here at the top, hypertherms under the ocean crust create plumes of hot water that rise to the surface and create global weather patterns. So this is an exciting new discovery that we found. You can see over here on this diagram of the Earth, there's cool areas and there's hot areas. Well, the same sun out there is shining on the Earth all the same. We don't have clouds over this whole area and not this area. What happens is we ask this question, how could the sun cool and heat these ocean surface waters along the equator at the same time? Well, the way it happens is the water plumes come up. Remember, hot air and the same with hot water rises. And so they come up to the top. And we know through our hurricane studies that just a 1 degree change in the top surface of the oceans is enough to expand the water, expand the air pressure and start these hurricanes which come and cause great havoc on our continents and affect the people that are on them. And so these anomalies with weather are actually now understandable when we start understanding what's going on underneath the crust. El Nino events are not caused by global warming. El Nino, you might have heard that term before. These are time periods when it's really hot, and there's a La Nina, I think is when it's cold. These events are global events, and they've never fully understand what's going on there because the pattern of the cooling and heating takes place over decades, actually. And this is all connected to the Earth, Sun, and Moon system because it's never the same. There's long cycles that are involved, and that's what's giving us this different weather pattern. So we can also go, we talked about the magnetic field to a piezo field. This is what Russ talked about a little bit earlier about the Earth having this so-called magnetic field going on around it, and we get shielded by the sun because of this field. The field's really important to us as human beings. If we didn't have it, the sun's rays would fry us. We get this protective field here from our Earth's energy field. But the problem is it's not a magnetic field. It's a piezoelectric field. One way to easily understand this is a film that has crushed rocks and 2 pieces of plastic on it. And when you take that film, it's called a piezoelectric film, and we move it back and forth. As a matter of fact, we put it in a vise here and we flip the end of it, and you can see the light bulb turning on. So this is a really small piece of film, not very much rock, and you can see the electricity being generated easily by it. Russ talked a little bit earlier about taking the rocks and actually rubbing together, and you can see light coming off it. Well, here's an example of electricity. You might have a barbecue at your home, and you ever push the button on it, and you see how a spark comes out and starts your barbecue, right? Well, that button you're pushing doesn't have a battery on it. It has a quartz crystal in there, and you're pushing it and generating electricity just by moving that quartz crystal in your barbecue. So this is what's happening in the crust. Remember a little bit earlier we talked about how the Earth's crust is constantly moving because the Earth is constantly spinning. It goes up and down. Well, what happens is this is a map of our geofield of the Earth, and this is the actual more correct representation of this electric field that's going on around the Earth. There's not just one dipole going on up and down. There's all these little poles. And what are they connected to? Well, they're connected to these things. These are highs and lows that are over the continent areas. So the continents have a much thicker, like I said earlier, about 36 kilometers compared to over here in the oceanic crust. The crust is 6 times as thick. So there's much more rock there to create more piezoelectricity. And this is where our energy field comes from around the Earth. And this is a completely new discovery that's never been known before. The geofield evidence, that we really don't have time tonight, obviously, but there's pages and pages of geofield evidence. The lightning is just one of the things. We have quotes by the meteorologists telling us they don't know where lightning comes from. Lightning actually happens when there's no clouds in the sky. So it doesn't come from clouds. Where does lightning come from? Well, one interesting way to see this is we now have photographers, and even everybody has their phone. We have our camera right with us almost all the time, so there's a lot more pictures being taken. This is obviously a volcano erupting. Why would lightning be going off right when a volcano is erupting? Well, we talked a little about earlier, the volcano is where we're getting friction, and that friction is creating heat. And the same friction is also causing our electricity going on. So this is, once we understand the truth, then we can start seeing this all throughout nature, everywhere we go. This is a quote from a researcher: "The connection between large earthquakes and electromagnetic phenomena in the ground and in the ionosphere is becoming increasingly solid." So this is exciting to see this new information coming forth, and we find this documented all throughout the book. Matter of fact, here's that Russian research we talked about earlier. What you have is 4 different places they've shown that when you're moving the crust of the Earth, you're creating electricity, and the Earth's energy field, or the geofield, is changing. All 4 of these diagrams are showing instances. This is a reservoir where they, like a dam, where they hold water, and they fill the reservoir, or they release the water coming out, and it's changing the energy field. The same thing happens with gas storage. It's amazing how much gasoline is stored in underground caverns. Tonight we're not talking about salt, which is a huge part of the universal model, but in huge underground salt storage tanks, they store gasoline and petroleum, and when they let it out and they put it back in, it's moving the crust of the Earth again, and that's, once again, creating this piezoelectric effect. The same thing goes on down here. When they actually have an earthquake, we see a change in the field, and here's another earthquake and another change in the field there. So the Russians have really been ahead on this information. We're going to move forward now a little bit into another exciting area, the hydroplanet model, because just like weather came from understanding correct geology, we now have something that most of us have seen. This is a crater. This is actually the most important crater, not just of the Earth, but our entire solar system. Why is it the most important crater? Well, when you drive up to it, this is the crater here in the background. This is the sign you'll see. It's the first proven, best preserved impact site on Earth. So now we have to ask ourselves, why is this such an important crater? Well, first off, it's called the Arizona Meteor Crater. They think this crater was made by an impact. Who thinks the Arizona Meteor Crater was made by impact? Everybody, except for a few UMers that have found out what we've taught about this. We actually have more information and more research done on this crater than any other book that you'll find in the world. I recently went there about a month ago, and there's some people looking over the side. You can see how big it is here. It's about a mile across, and they have a visitor center. You can go and see the crater yourself. But if you go inside the crater, you see all these exhibits and telling us, why is this crater so important? The astronauts actually went there when we went to go to the moon. We know there's craters on the moon, of course, so they thought, well, we'll go down in there and find out what it's like being in a crater. So it's got a long history behind it. One question we ask is, why is the origin of this crater important? Why should we care? Okay? Well, the reason that we should care about this crater is because the age of the Earth was first made assuming that this was an impact crater. I don't know how many of you know, but if you go to school, or if you remember when you were in classes, they teach today the Earth is 4.6 billion years old. That age came from this crater. One of our presenters, he showed me this the other day. He's taught classes for a couple decades, and he said all the kids today, they love to pull out their phone when you tell them something and Google it. They want to test the teacher and find out, well, is that really correct? Well, if you Google the age of the Earth, what you're going to find is this figure up here, 4.5 billion years old, and Of course, down here, this is the current worldwide scientific consensus. How do you determine the age of the Earth? This is a related question people like to ask. They also like to ask, why are meteorites used to establish an age for the Earth? Well, it's actually very simple. The best estimate, and this is once again right from Google, the best estimate for Earth age is based on the radiometric dating of fragments from the Canyon Diablo iron meteorite. This happens to be the Arizona meteor crater. Or the meteorites that they say were found around the crater. From the fragments, scientists calculated the relative abundance of elements that formed as radioactive uranium decayed over billions of years. Now there's a problem with this. What would happen if what was calculated with this uranium dating system was incorrect? It turns out that the uranium radiometric dating system isn't even used anymore today because they know it's so wrong. But what's even more important that nobody's known until now is that this date came from the assumption that the rocks found around this crater came from space. And they didn't. We're going to just briefly, for the sake of time, I'm going to go over just these top 3 really briefly. But as you can see, all 11 of these are detailed in the universal model. That's universalmodel.com. You can go on there, and this is in the hydroplanet model, and find these answers. The very first one, the lack of impact glass. These are evidences against the crater being impact crater. Well, that impact glass happens to be very, very important. This is another picture of the crater and a so-called meteorite that was found on the outside of the crater. They never found any meteorites on the inside of the crater. And I'm going to explain why in just a second. But the impact glass is what we want to talk about right now. And if you look down here a little closer, it says, without impact, Earth, Mars, Venus, and Mercury wouldn't exist. This is how much impact theory has taken over the understanding of how planets are made, of how the Earth was made. They think it was all made by impact. The problem with this is, this large of a crater, the physicists clearly understand that the rock that would be, the size of the rock that would make this size of a crater would be huge. I think it was 300,000 kilograms is what they calculated. The problem with that is large rocks like that, when they come through our atmosphere, it's traveling at such a high speed, it's greater than 10 kilometers per second. So they call this hyperspeed. And when it's traveling that fast, it's a couple seconds and it's right through the atmosphere. It doesn't have any time to slow down. So when it hits the crater, what it actually does is causes an explosion so strong that it's the same as a nuclear explosion. Now what I've done is taken some of the earth here and we simply took an acetylene torch and melted it. And what happens when you melt the earth, it's like in the sandstone inside the crater, you can see right over here, this green area, you have cooled green glass. This is what forms. Russ explained a little earlier, when you take quartz rocks and melt them, I'm wearing glasses right now, and this glass came from sand, quartz sand. It's the same type of sandstone that's around this, inside this crater. It's the #1 mineral on the continents, the constituent is quartz. And quartz turns to glass when you melt it. Every experiment that researchers did inside a laboratory when they did high speed impact caused the inside of the crater that was formed to be lined with glass. How much glass do you think we found on the inside of the Arizona crater? None. Matter of fact, this is the Trinity atomic explosion. So this was back in the 1940s in New Mexico. Up on this tower, they exploded the very first atomic bomb, and it created a crater here. This is an aerial looking down on it. Here's a guy standing. That's a black and white because it was done back in the 1940s. But that's melted glass. He's standing on the entire inside of this crater because everything was moved out so quickly The friction caused it to melt and make glass. This is critical in understanding that all high-speed impact craters would be lined with glass, and of course the Arizona crater is not. Now, the meteorite model, we go into detail explaining not only does the glass have to be melted in the crater itself from the sandstone and the rock inside the crater, but the meteorites themselves have to be melted. Amazingly, not only would they be melted, but they'd be vaporized. It gets tens of thousands of degrees temperature, and you only need 1,700 degrees to melt quartz and meteorite type rocks that have iron in them. And this particular rock, what they believe was a meteorite, when we took an acetylene torch to it, you can see down here, it's a lot like melting iron beams, or if you take nails and melt them, they're beads, okay? Well, the researchers that found these iron rocks, we call them iron ejectites, not meteorites, around the crater. Guess how many they found that looked like this, that were melted? 0. In the laboratory tests, when they did high speed, the iron particles that they used, when they hit the impact, they not only melted, but they actually vaporized. So that means they just, when they vaporize, it turns into a vapor, and then it comes down in a mist. And so it's very obvious that if any rocks that had come from space, they would have been vaporized and been melted, and there is no vapor residue, and there's no melted meteorites at the Arizona crater. So there's one other example, and this is the third one we're going to talk about right now. Well, no, actually, we're going to go into the evidences of why it's a hydrocrater right now. So the top 3 here is what we're going to discuss. The first one is the water source evidence. Now, the crater was named after a guy named Barringer, and you can see a picture of him here, right here, and he was the first person that tried to show that this was an impact crater. And this was back in the early 1900s. And he had a lot of money from investors spent to drill down in the crater, and he thought he was going to get rich by finding all this iron, and they never found it. But instead what they found was this. In passing, I should say that it was found impossible to sink our main shaft more than 22 feet. And they drilled over 1,000 feet, or about 25 feet below the water level, because of the peculiar quicksand formed by the water-saturated silica. Notice water saturated, which we encountered. Also that, in my judgment, it will be impossible to properly explore the depths of the central portion of the crater until we have removed the water, which we now know fills the lower portion. All below this crater is water. It's still there today. The visitor center has a well down there, and that's where they get the water from. So right below the crater is water. And of course, this is what you have to have. So what do we need to make water into steam? We need heat, right? Well, where do we get heat from? We get it from friction. Guess what the crater, this is the black area, is from a journal article about the Arizona hydrocrater, we call it. And as you can see, there's tear lines in 4 different places. And those tear lines, this creates 2 fault lines. This is not my drawing. This is from their drawing. And it shows a cross right in the middle of the crater. I haven't found this in any of my other research. I've actually researched over 100 craters exist about 3 hours from my home in Arizona. I can drive to 100 craters. I've been to them all. 99 of them, geologists believe, were made by a steam explosion. They're a hydrocrater. One of them, they say, is an impact crater, this one. And it turns out they were wrong. It's also a hydrocrater. So now we're going to give you what I call a smoking gun or a definitive proof about this crater. And remember that it's really important because this is where scientists begin to give the age of billions of years to the Earth. All their other previous dating methods. We actually have a whole chapter called the age model, and we show a lot of deception that took place over the years. And we go into detail showing these old journal articles, the kind of experiments that were done and not fully explained. But it all comes back to the very first time they came up with this 4.6 billion year number was from the Arizona crater. And it turns out that the diatreme, this is a word that's one day your children or grandchildren, they're going to understand this as much as they understand words like photosynthesis or an easy word in science or something that would be a process that takes place. But the diatreme is such a simple thing. What it actually is this area underneath the crater. And we're going to look at that right now. So this is a diagram that was made by an individual called Shoemaker, and I call it the Shoemaker question mark diagram. When I first saw this, it was about 15, 20 years ago, I guess, when I first went to the Meteor crater, and we call it Arizona Hydrocrater now. And I saw this diagram on the wall that they had in the visitor center. And as you can see, all these little, they were backwards C's at the time when I looked on the diagram there. It didn't have the little dot on the bottom of the question mark. They were just little C's, and I couldn't figure out what are all these little C's on here for. And it turns out the reason those were there is Shoemaker and others used this diagram to claim that cores of ordinary siltstone and sandstone of the Supai, this is the deposit layer here, were obtained at depths of 700 feet or deeper. What he's saying here is below, this is the actual crater here today, this area right here, okay? And everything below this, and you can see these shafts, that's where Shoemaker drilled, okay? So all this area here below it was supposed to be ordinary siltstone once they get down to here. They thought once we get down to here that all this area would be siltstone, and only this area right here would be crushed from an impact. This is another diagram that Shoemaker made, and as you can see, when you have an impact coming from space and it hits the surface like this, it creates a circular area underneath it right here. All that circular area is shocked quartz. It's all been crushed and banged up. Over here, this is a computer-generated diagram, and they show the same thing. Well, this is what we call a concave shape here. And we found, very interesting, in 1975, these three individuals, they believed the crater was an impact crater, and so they did this very important article that everybody's missed. This is one of those little pieces of the puzzle that's off over on its side, and it doesn't connect to anything in modern science. And what these individuals found is amazing. So this diagram is right out of their journal article. All these black areas are theirs. Now I colored this area red inside here, and they call this the fractured zone. And reading their article, you'd think, oh, well, yeah, look, it's concave. It's just like it came from up here, right? And it made this impact crater and crushed all this quartz underneath it. Well, it just so happens you have to look way over here, this little yellowed area. What's the word say? Inferred. Yes. This is the boundaries inferred. Okay? So the point is, that's what they were thinking it might be. Well, to find out, what these three researchers did is they took TNT, they did explosions on the top of their crater, and they put seismic measurement detectors all around the crater. And from this, when sound travels through crushed rock versus solid rock, it goes much quicker through the solid rock. You can see it going through a crushed rock that has to go all the way around. And so this causes it to go much slower, and they could easily map underneath this crater. Where is it crushed and where is it not crushed? And guess what they found? First off, they said drilling by Barringer and his associates did not pass completely through the fractured zone. Oh, they thought they did. Barringer had thought they did, but these guys found out they did not. Remember, this is Shoemaker's claim, And here's what they actually found out was over 2,625 feet were fractured. And here's the smoking gun diagram they actually put in their book, well, in their article. Once again, this is there. All this black area is theirs, the eye colored in the red. As you can tell, it's not a concave fractured area underneath this crater. It's convex. This shape, what you're looking here, is a funnel shape. That's what a diatreme is. This diatreme is underneath all these craters. And the bottom down here is kind of fades out because their seismic couldn't go beyond that. They knew it with the crushed area even went way down here farther. And this is because it's a pipe. The pipe went all the way down to the area where the heated steam came and blew up the debris up on top. So this is unequivocal evidence. You don't have a rock come from space, land on an X, and create a diatreme underneath the crater. It's impossible. And so this is really fundamental new information that changes our whole paradigm of modern science because it helps us understand the cratering process. This quote is by Grove Carl Gilbert. He was actually the first geologist, we got right down here, the original ones, who was correct stating that the crater was a steam explosion crater. We have a picture of him in the book on his horse in the late 1800s going and looking at this crater. And this is what he said. In the testing of hypotheses lies the prime difference between the investigator and the theorist. Okay? The theorist was Barringer and all these other scientists that are choosing to think it was an impact crater without having the evidence. The investigator was somebody like himself. The one seeks diligently for the facts, which may overthrow his tentative theory. The other closes his eyes to these and searches only for those which will sustain it. This is really one example of what we found in all the fields of science. And why have we had to go from geology to archaeology to biology to physics to chemistry, paleontology? The reason we had to go to so many fields is because the answers to fundamental questions are found in a whole other field. And unless you understand this astronomy over here, you'll never understand over here this geology. And a lot of times the geology isn't understood unless you understand microbes out of biology. The colors in rocks actually come from microbes. And we document this in the book. And it's fascinating to see each of the fields of science interconnect like this. So the hydroplanet model is the longest chapter. It's about 250 pages in the book. And it leads us right into the universal flood model, which is the next longest, about 230 pages in the book. A lot of people think right off the bat, well, where did the water come from? You know, how could there be enough water to cover all the mountains? Remember, Mount Everest is 5 miles high. That's a lot of water, way more than in our oceans today. Well, you're looking at a paperclip floating on water. Anybody can do this if you'll set it on it flat really carefully, you can get it to float. And in fact, a piece of paper floats much easier on water. And that's about the thickness of our crust of the earth comparatively when you put a sheet of paper on a plate of water. It easily floats. And that's what our continents are doing. Surface tension keeps our continental plates floating. However, they're actually pulled out more on the equator area. And what happens is, I think it's about 50 kilometers more that they're pulled out on the equator than that they are at the poles. And that's because if we take a rock and put it on the end of a string and we spin it around our head, we'll find that the rock will stay way out there as long as we spin it fast enough. But what happens when we slow the rock down? Well, the rock falls in towards us, right? I mean, we've all done that, spin something, and if you do it slower, it comes back in. Well, we actually give in the universal model the mechanism in this particular chapter of how the Earth's spinning was affected. And it actually was affected by a large celestial body such as a comet. And the comet that came close by the Earth happened 4,361 years ago. We actually have evidence that goes into detailed documenting not only the year, but actually the very month that the universal flood took place. That water is real important to show that it came from underneath the crust. We showed this diagram here a little bit earlier. Because if you take the water that's in the atmosphere, it just didn't rain for a couple months and all the water, because the atmosphere moisture is only about an inch thick if you put it on all the continents. So the rain is not where the water came from. Yes, there was a lot of rain during the flood, but the flood actually came from the water that's underneath the crust. The geologists already acknowledge, all over you'll find them acknowledging the plates floating on a liquid. They just don't know what kind of liquid. Well, this is the liquid. See, this fault line is this crust fell down because a good example is when you have a top and you're spinning it on a table. It doesn't spin forever, does it? It slows down. Why? Because of friction, okay? And that slowing down causes eventually to fall over. Well, the same thing with the Earth. The Earth is spinning on its axis, and it turns out, I don't have time to go into it tonight, and it's actually in volume 3, we discuss why the Earth's spin is on an average rate constant. It's the most important constant of all constants is time, and the Earth's spin rate is how we measure time. But tonight what I'm going to explain to you is that spinning rate was slowed down by this comet that came by the Earth. And the comet, most of you might have heard of Halley's Comet. That was like every 78 years, I think it comes by. And until recently, astronomers didn't know that we have comets that are thousands of years in their period. Is it Sedna? Do you remember which one there is, Russ? Yeah, Sedna, I think, is it. So that is a comet that has a period of 12,000 years. So 1/3 of its time period, 4,000 years, is enough. And this could have been the flood comet or another comet like it that came by the Earth. It didn't have to hit the Earth. It didn't have to even come really that close. It just had to come close enough, like the moon does, to affect the crust of the Earth. And by the way, that particular comet's about the size of the moon. And so when it did that and it caused the Earth to start to wobble and to slow down in its speed, what happens is it's like that rock you're spinning around, and when you slow down, it falls in on you, and that's what happened to the crust. The crust fell down, which caused this water down here to squirt out into hydro fountains. Russ talked about this one earlier. I'm just showing a little more blow up. This Enceladus hydro fountain, this moon, by the way, is only 300 miles across. I think it's mostly water, what they believe. Some of these moons, they believe, are almost all water. And it's just not talked about because it doesn't fit in the magma paradigm that we're taught in school. But this, from heat friction alone, created a plume that was longer than the 300 miles across the planet. Just amazing to think about that we had a spacecraft there filmed when this took place. But this is the type of fountains that happened in the universal flood. You can see this coming out of the Earth here. This is our diagram we made. But when the fault lines bursted and hydro fountains came out, it created a tremendous upheaval in the Earth when the plates dropped down. This is another diagram. It shows, here's the water that's underneath the plate. This is the continental plate right here, and this is the oceanic plate here. And water from below is forced through the cracks in the crust with the heat and pressure. Now, when the water comes through, Russ explained a little before what the hypertherm is, but he didn't really go into that much detail. The detail is really a recipe. You have to have water, you have to have the heat, you have to have pressure. There's also gases that are required. There's also some other minerals, dissolved minerals that are required. And when you have the right recipe, it's just like making cookies. You can make it every time, you can reproduce them. And so we found out how to do this in making rocks, which of course, I'm going to end here talking about fossils in a minute. But first we're going to talk about fossil hydro fountains. because when the water comes up through these fountains, these are pipes through the crust. When you have the right pressure and temperature, what happens is some of the silica that was dissolved in the water becomes crystallized, and it literally creates a pipe of rock. Well, this pipe of rock, this is my researcher right here standing down below, and you can see how big this is. All the sediment that was around it got washed away. And these are fossil hydrofountains, we call them, and you can see them standing up like this, and they go deep down in the ground, and all the sediment around them that's been washed away because it was not heated at the same temperature and pressure. And these are actually found all over the world if you'll go and look, but they've been anomalies to modern science. Well, if you go down to the bottom of the ocean right now, we can find the same type of environment that was on all the surface of the earth, all the continents, when the universal flood happened. If you go to areas where there's a fault line underneath the ocean floor, this happens to be Tag Mound, a very important mound that has direct evidence for a bunch of things that we talk about in the universal model. You can see pyrite here being created, and hydrite, that's a type of salt, quartz and basalt. These are all being formed on this mound. Another fascinating thing that was formed on the top of this mound is something called chalcedony, okay? And that's right here on the surface, because what came out, this is at 338 degrees Celsius. Keep in mind that rocks are made at 1700 degrees Celsius, excuse me, not made, but they're melted at 1700 degrees Celsius. So 338 is way below that temperature. But because this is under several miles of water, and we have a ship up on top of the ocean, it costs millions of dollars to send a pipe all the way down to the bottom and then drill into this mound. And so this hasn't been done. This is like the best example that's been done so far. When they did this, they found all these different rocks being formed right now in this environment. So this is actual evidence of everything we're telling you tonight as being correct. But what's amazing is right on the surface of this chalcedony they found, you can find today all over the world if you know what you're looking for. In deserts all around the world, you'll find this surface chalcedony. This one section here is the chalcedony. It's a swirl-like quartz substance. So a lot of the chalcedony is actually in agates and really pretty rocks that are collected. And this one was formed right on top of a hard piece of rock. But a lot of the little swirls that you can see here, these were formed on soft sediment. And that soft sediment is underneath. On the bottom side, you can see how different they look. Okay, they're kind of rough and coarse, and that's because it's against the ground. On the top here, some of them even have crystals growing. It's smooth. It's a totally different texture. These are from Brazil, but you can find them right here in Nevada and Arizona. I've gone all around and found these, and they're in the desert right on the surface. So we call this surface chalcedony. And you'll find them if it's an area that has not been disturbed, which a lot of the deserts for the last 4,000 years has not been changed since the flood took place. You'll find these sitting just like they were when they were formed. When all the waters abated and went away, if this area had not been affected by the waters, in some places it went down slowly, in other places there was rivers and it was very rough. But in these areas, you can find this sitting right on the surface. Matter of fact, another very important mineral deposit found on the surface are these geodes. And geodes, one researcher found, this is how many feet below the surface, that it was the area inside the geode that's open, okay, got less and less as you went deeper, deeper. But remember, this is only the top 8 feet. You don't go down in the Grand Canyon and find geodes. You also don't go down the Grand Canyon and find petrified wood or bones of any animal. Think about that. All these layers, there's no area that's been more studied than the Grand Canyon in the world, geologically. And they don't find one bone, one piece of petrified wood, or one geode. The universal model explains detail why that is and how important that these are surface marks. These are called thunder eggs, but they're really geodes, and they're formed only on the surface. We talked about this a little before. This agate is kind of like this calcine we were just talking about. And the same thing goes with these fossils. They're found only on the surface. This is an amazing quote that we found lots of researchers discovering this, and notice what they found. Up to 95% of the Earth's marine species disappeared at the end of the Permian period. This is a period that we explain later on didn't actually take place millions of years ago, but it's during that time that they think some 70% of the land species, including plants, insects, and vertebrates, also perished. It's arguably the single most important event in biology, but there's no consensus as to what happened, says paleontologist Andrew Knoll of Harvard University. So 95% of the marine species and 70% of the land species disappeared. They already know this. They acknowledge this. And the reason they know this is because the fossils they find are not the same species that are living today. Now, some of them are. Actually, some of the species that are living today, we find their same fossils, but a lot of the species got killed and they don't exist anymore. Evolution is something we talk about in the second volume, and it's important to recognize that there has never been a scientist that has found in the laboratory or in nature a new species being formed from another species. This is called macroevolution, and we go into detail with many examples showing this in that chapter. So something that's really important is the petrified wood we talked about. This is the Petrified Forest. I went there about a month or so ago, and these are some images I took. These trees are solid rock right now. And remember, we didn't find any of these over in the Grand Canyon. It's just a couple hours away. And we have to ask ourselves, well, why not? You know, how does a piece of wood get buried and not decompose? When have you ever seen a piece of wood in your backyard or in a forest not decompose in the ground? Bury it however you want. It deteriorates. The microbes that are in the soil, and they're in all the soils around here, decompose the wood. Now, there's very few areas. You have to go to the North Pole or South Pole. It has to be really cold or an area that there's no oxygen for the microbes not to exist and be able to do this. So almost everywhere, wood decomposes as soon as it's buried. Yet in every state of the United States, we find petrified wood. It's all over the world. You just have to know where you're going. Right here in Utah, in Nevada, I found petrified wood. You can go up in the mountains here and find it all over if you know what you're looking for. So the question is, where does it come from? How is it formed? Well, the answer comes from the universal model, because this is a lot going on in here, and I'm not going to go into a lot of detail, but I'll explain a little bit about it because we're almost finished up here. This is an experiment that we explain in the second volume, where we take apple wood from my backyard off a tree, and we put it in this autoclave that we had grown quartz in, and we turn it into petrified wood. And we do this in, matter of fact, the first petrified piece of wood is right there. It was run 55. I think we had 74. There's run 74 right there. So it took 3 years and 74 runs. Each time we did one of these, it took us at least a week to clean it all out and do it all over again. It was a long process. This is the first quartz geode that we think that was ever made. And you can see the crystals growing there inside our autoclave. So the point is we found the recipe, the temperatures and the pressures that it required to grow rocks, and therefore petrified wood being a rock, we found that we could also turn the wood into stone. But you had to have the recipe, and the recipe requires 5 miles of water. That's about 13 to 14,000 psi. It requires 375 degrees about of heat and some other things. And once you understand this recipe, then you're able to actually put this into practice and show how this petrified wood got made all over the surface of the Earth. You don't go down deep in the layers and find petrified wood. It's only on the surface. And the same with all the fossils. Dinosaur fossils are no different. They're made out of rock, just like the petrified wood is. So now we actually have an answer for all these questions that your kids are, if they haven't asked you, as soon as they start talking and find out about dinosaurs, they're going to ask you where they came from. And this book can explain to you for the very first time how these fossils and the petrified wood got formed.